In these videos, we're just going to go through a couple of examples looking at the existence and uniqueness theorem for linear DEs. So this theorem says that if we have a DE that has the form dy dt plus p of ty equals d of t, y of t naught equals y naught. Okay, so a standard form linear DE with an initial condition, then as long as the coefficient functions p of t and g of t are continuous in an interval containing t naught, then on that whole interval, we are guaranteed a unique solution exists. And that existence doesn't depend on the value y naught at all. So as long as p of t and g of t are continuous and the interval that we're looking at contains our initial time, then we're guaranteed a unique solution to this problem throughout A to B. And we don't need to think about y naught's value at all. Okay, so the way that we usually approach this is we think of taking the real number line and we look for the discontinuities of P and G. Okay, so we would mark, say, if we're only continuous on A to B and not at A and not at B, then we mark these discontinuities and we look for the interval that contains our initial condition, our initial time. And so we're guaranteed a solution exists on this interval. A reminder of why this is true was that we actually were able to build our solution explicitly using integrating factors. And that solution was works, makes sense, as long as we have P and G are continuous. So let's try this out with a couple of examples. So in the first example here, we're given this DE, initial value problem, and we want to find the largest interval on which we have a guarantee that we have a unique solution existing. So if we take a look at this, the first thing that we're going to notice is that this is a linear DE. This guy is linear, so this theorem is going to apply. Okay. We need to start by putting this into the standard format for linear DEs. So we're going to divide through by this factor, multiplying dy dt, which is t minus 2. So dy dt plus log of t over t minus 2 squared times y is 1 over t minus 3 times t minus 2 squared. Okay. And so now these coefficient functions, p of t and g of t, we can identify. What we're going to do is figure out everywhere where these functions are defined. And we're going to also look for where they're continuous. So for this type of function, where it's defined and where it's continuous, agree. Here we know y of 4 is equal to 1. Okay. So looking at our number line, places where p of t and g of t don't exist, are not defined, include t equals 3, t equals 2, and we think of the natural log function, this is only defined for t values bigger than 0. So 0 is out, and so is everything smaller than that. All right, and so what we're going to do next is take a look at our initial time. Okay, so this is saying that our solution needs to be around when the time is equal to 4, because when the time is equal to 4, we need our output to be 1. So let's draw that in. Here we have that, we have the 0.4, that's our y value, is 4. Nope, that's not what I meant to say. Our t value is 4. Our y value doesn't matter at all. We can completely ignore the y value entirely. And if we look and we see where is where is continuity guaranteed that contains the this t value of 4, we see that we go from 3 all the way up. And so we have a unique solution exists on 3 to infinity. Great. Let's take a look at this next example. I'd like you to look it over, pause the video, and try this out. So we want to find the largest interval on which a unique solution to this initial value problem is guaranteed to exist. And like the previous one, this one is a linear DE. Okay, pause and try this out. So there are a couple of things you should have noticed. So first, this is already in standard form. Okay, so here we have P of t is t minus 2 squared, and G of t is sine of t. And these functions are both continuous everywhere. Okay. What that means for us is that when we draw our number line and we put in the places where our functions are not continuous, we're not breaking up this number line at all. Okay, and so that means that a unique solution to the initial value problem. Oops, let's draw in this dot for our initial condition here was 4. It's that time. Okay, but there's only one interval. Okay, so a unique solution is guaranteed to exist for all for all times. So for t between negative infinity and infinity. We're not going to see solutions crossing. We're not going to see solutions coming together. We always and our solutions are going to last for with domain negative infinity to infinity. Great.